Okay, we're going to look at number 30 on page 168, which has the cauchy Euler equation x squared y double prime minus 5xy prime plus 8y equals 8x to the sixth, where we have initial conditions of y of 1/2 and y prime of 1/2 are to be equal to 0. So again, remember when we have a cauchy Euler equation, what makes it cauchy Euler is that the degree on the monomial in terms of the x is the same as the order on the derivative on y. So see, we have x squared and a second order derivative, and x to the first, a first order derivative, no x, and just the y function, so no derivatives. All right, it's a non-homogeneous equation, so we'll use variation of parameters in this case to solve. To use variation of parameters, the first thing we have to do is find that complementary solution, which in this case involves solving the auxiliary equation. Again, remember this term here is coming from the fact that our guess for the solution to the homogeneous equation is of the form x to the m. So when we take the second derivative, we'll have an m that pops down and an m minus 1 that pops down. So we have to pay attention to that. It's not just as simple as writing down the characteristic equation for constant coefficient homogeneous equations. This simplifies to m squared minus 6m plus 8 equals 0. That factors nicely. M minus 2, M minus 4. So we get solutions of 2 and 4. These are distinct solutions, so our form for our complementary solution will be c1x squared plus c2x to the fourth. We'll now use GeoGebra to help us out with doing variation of parameters. So let's flip over to GeoGebra. So I didn't open it up yet, so let's do that. So remember, for GeoGebra here, we're going to need to to use a variation of parameters. We'll need to define our functions for our fundamental set and then solve our system using Cramer's rule. In this case, our fundamental set was x squared and x to the fourth. So we'll set our f of x equal to x squared, our g of x equal to x to the fourth. We also need to figure out, set our function for our right-hand side of our equation, but just to remind ourselves, this was a cauchy Euler equation. The coefficient on the highest order term here was not 1. So before we define our h of x back over in GeoGebra for our variation of parameter solution, we need to divide both sides through by that x squared. So when we do that on the other side, we'll get an 8x to the fourth. That will be what we want to use for our h of x. So typing that in over here, our h of x equals 8x to the fourth, not 8x to the sixth. So we need to divide through by that x squared. All right, so going over to our spreadsheet now, let's define our matrices like we always do. Our f and our g, and our f prime, and our g prime. Let's copy these down a couple of times so that we can replace our first column with 0 and h in the first matrix, and the second column with the second matrix. And let's go through and define all of these. So we got our M1, we've got our M2, and we've got our M3. We use Cramer's rule again, so we'll take the determinant of M2 and divide that by the determinant of M sub 1. And just to save some time here, we'll copy this down, change the 2 to a 3, and get those. So remember, we're using Cramer's rule to solve the system. These are the solutions to u1 prime and u2 prime, so we need to integrate both of these. So we'll integrate number 4, and we'll integrate number 5. And then these are the ones that we need to multiply by f of x and g of x. So we'll take number 6, f of x, and add number 7, g of x, and get that. So this now is our general solution to the non-homogeneous equation. Our particular solution, as we could read from the GeoGebra, was x to the sixth. so that our general solution is c1x squared plus c2x to the fourth plus x to the sixth. Of course, again, we wanted to have these subject to the conditions y of 1/2 equals 0 and y prime of 1/2 is also equal to 0. Let's go over there and solve that using GeoGebra. Found a little quirk earlier with GeoGebra that if I just use our function and you leave the c1 and c2 that it defined, it didn't like solving for the c1 and the c2. So when I define a new function j of x here, I'm going to write it as a x squared, b x to the fourth, and x to the sixth. And then we'll solve for a and b. Remember to put spaces in between the a and the x, or in the b and the x, so it knows that you want multiplication there. So now we want to solve the system. We want j of 1/2 is equal to 0, and j prime of 1/2 is equal to 0. And the variables that we're interested in are a and b now. And we get 1/16 for a and negative 1/2 for b. So going back to write this down, our y is equal to 1/16 x squared minus 1/2 x to the fourth is plus x to the sixth. That's our solution for y.